Welcome to another ultimate review. This time we're going to focus on significance tests. For a lot of students, this is one of the toughest types of problems, and it actually could really hinder your ability to get that perfect 5 on the AP Stats exam. So if you know it, trust me, you're going to do very well. Don't forget to like and subscribe. Let's dive right into it. So what is the overview? Now keep in mind the significance test is a form of inference. Inference is using a sample statistic to make a judgment about a population parameter. Let me give you a couple quick examples, right? So I'm going to use a proportion from a sample p hat to make a judgment about a population proportion p. Or I might use a sample mean x bar to make a judgment about a population mean mu. Okay, simple and easy. But how are we going to do that? Well, first you need to get a sample proportion or a sample mean. So you got to start off by getting a sample. Then what you need to do is actually compare that sample to all other samples just like it. Same sample size, drawn from the same population. And that is, of course, why we need a sampling distribution. So a sampling distribution of a statistic would be a picture of all possible p-hats, not just ours. And then the idea is we can think about where does our p-hat fall. Now we know smack dab in the middle of a sampling distribution for a sample proportion is the true population proportion. That's because the mean of all p-hats is the truth. We learned that back with sampling distributions. And we also know that there's a standard deviation there as well. But the key thing I'm trying to get across is, where is our sample proportion? And that's what we're going to figure out, right? If we find out that our sample proportion is really close to the truth, well, then it's not significantly high nor significantly low. But if we find out that our sample is way over here, that would be significantly high. And that's when we would say, well, wait a minute. Maybe our judgment, our thought about this population proportion is actually wrong. So it all comes down to figuring out where does our sample statistic fall within that sampling distribution. And I can do the exact same thing with sample means as well. We, of course, start off with our sample mean, but then we got to figure out where does that sample mean fall in the sea of all possible sample means, which is, of course, the sampling distribution. Now, once again, smack dab in the middle is the true population mean. That's because the mean of all sample means is the true mean. And then again, we want to really see where does our sample fall. Does it fall just a little bit below the mean, or does it fall a lot a bit below the mean? Now, to figure out where you fall on a normal model, of course, you need a z-score, or William Gossett introduced us to a t-distribution. Remember, t-distributions are better for means when we only know the standard deviation of our sample. That's kind of a whole other topic. I don't want to dive too far into this video, but just note that when you're working with means and the only standard deviation you know is that of your sample, then you're going to actually be using a t-distribution. But the good news is it acts and behaves just like the normal distribution. All right, so that's kind of the overview of what you're actually doing when you conduct a significance test. Now let's talk about the different types. There are several different types of significance tests. We have a one-sample z-test for a population proportion. That is when we're trying to use a p-hat to make an understanding or a judgment on a p. We have a one-sample t-test for a population mean. That's when we're going to use a sample mean to make a judgment about a population mean. We have a two-sample z-test for the difference between two population proportions. That's where we're going to use the difference between two population proportions drawn from two different samples. And we're going to make that, in and of itself, that's one number. I know that looks like two numbers. Let me kind of slow down here for a second. So when we're looking at the difference between two proportions, it's the difference. So it ends up being a single number because the difference of two numbers is one number. But it's the idea that we have a sample from one population, a second sample from a second population, and we're trying to see, hey, wait a minute, what could that difference tell us about the true difference between the actual true population proportions? Okay, hopefully that makes sense. We can also do a two-sample t-test for the difference between two population means. So once again, we're looking at a mean from one sample minus a mean from a second sample. That's a difference of means. And what that can tell us about the true difference between the means of those two populations. We can also do a one-sample paired t-test for the mean difference. This is when we have paired data. Now, when you have paired data, you actually don't care about the individual values. All you care about is the mean difference. That is not the difference okay, let me slow down here again. That's not looking at the difference of the means. It's looking at the means of the differences. So again, when you have paired data, all you actually care about are the differences, and then you're looking at the mean of those differences, and we're making a judgment about the mean of all differences if we were to envision all possible pairs. Again, if you're looking for a ton more detail on all these things, I have plenty more videos that go into them specifically, and I'll link them at the beginning of this video if you want to actually go and find them. Then we also have our chi-squared test. We have chi-squared test for goodness of fit, homogeneity, independence. Those do follow very similar procedures to what I'm talking about right now, but they don't use the normal model. They use the chi-squared model. So things are a little bit different. But again, I have a whole series of videos over all of those that you could find up in the links here as well if you're interested in that. All right. Now, the good news is all tests have 4 parts. So when you understand, hey, this question wants me to find evidence of a significance here or there, like you clearly know, and I hope you've done a good job learning so far, that you know that you need to do a significance test. The good news is there's 4 parts. So if you just kind of, go slowly through the 4 parts, you should do really, really well. So let's kind of review those 4 parts. The first part is to name the test in context and state the hypotheses. This is where you would say, oh, I'm going to do a 1 sample Z test for the population proportion of gummy bears that are green. Or I'm going to do a 1 sample T test for the mean time it takes to go to the store. I don't know. I'm just making things up. But again, you're incorporating the name of the test that I just kind of showed you with the context of what the heck the problem is actually talking about. Then you also need the hypotheses. Okay, now here what we're doing is we're acknowledging what type of test we're running. So really take the time to read the problem. Decipher if you're working with proportions or you're working with means. Okay, are you working with 1 sample or are you working with 2 samples? Because if you're looking at 2 samples, you're looking at the difference. So that'll kind of give you a direction in terms of where we're going. And, how do you know that? You got to kind of read the problem. So take the time to really read the problem once or twice. Hopefully you at least read it once, right? All right, then you want to also develop the null and the alternative hypotheses for your particular problem. Let's look at a bunch of different examples for null and alternative hypotheses. So first here, I'll highlight in yellow. These would be hypotheses or what they could possibly look like if you're working with a 1 sample Z test for a population proportion. So maybe we read that 23% of gummy bears are green, and oh no, we're thinking that it might be more than 23%. So that's where the null is like, no, everything is fine, status quo, the truth is 23%, and the alternative is no, we think it's higher. The alternative hypothesis is always what you're looking for, right? Nobody conducts a test hoping that what they're looking for is wrong. You're always hoping that your alternative is correct, and maybe you figured out you're right, or maybe you figure out you're not. But it is what it is. But the alternative is always what you're looking for. I'll highlight in green here. This would be a 1 sample T test for a population mean. So maybe you say, I read that the mean weight of a bullfrog is 46 grams, but boy, oh boy, I think that it's less than 46 grams. I think that global warming is causing bullfrogs to shrink or something like that. So again, the alternative is everything's the way it should be. It says it was 46. I'm going to believe that. And then the alternative is that, no, I think it's less than 46. But notice that we don't use any X bars. We don't use any P's here. The alternative and the null hypothesis are always in relation to the true population values, because that's what tests are all about. Your samples are actually what you know. Like the samples is what you took and you see. Like that's not up for debate. What's up for debate is what might be true about the population parameters. All right, in red here, this would be, or pink, I guess, that would be the null and alternative. This would just be an example if we're looking at the a 2 sample Z test for the difference of population proportions. So maybe here we're looking at the proportion of men that smoke versus the proportion of females that smoke. And the alternative would be, nah, they're all the same. There's no difference. It doesn't matter your gender, right? Proportion of men, proportion of females that smoke is the same. And the alternative, again, you got to read the question. Maybe it says, oh, we think men are higher. We think women are higher. Or we actually don't care who's higher or lower. We just care that there's something different. Now, that's actually what we would call a 2-sided test, because if all we care about is that the 2 proportions are different, then we don't care who's higher or who's lower, so we call that a 2-tailed test. Whereas if we go back over here, I only care about being greater than. That would be a 1-sided test on the upper side, because that's greater. This would be considered a 1-sided lower test, because all I care about is being lower. A couple more examples here. Here's another one I'll highlight in blue here. This would be a 2-sample t-test, the difference of population means. So we'd say, oh, the mean time it takes a male police officer to finish an obstacle course is the exact same time as the mean time for female police officers to finish an obstacle course. The null would be no difference whatsoever. And the alternative would be, oh, I think the mean time for male police officers is longer than female police officers. So we would use a greater than sign there. So again, that'd be a one-sided test. But again, you got to read the question to know what you're doing. Now, if you're doing one of those special paired t-tests I was referring to earlier, here you would say, hey, listen, I think that the average difference is 0, meaning there's absolutely no difference between these pairs. Before, after, twin A, twin B, there's no difference between these pairs. And the alternative would be, no, there is a mean difference. I think there is a mean difference that's greater than 0. So you get the idea here. These are all just examples to try to make sure you see, but don't use any X bars, no P hats here. We want to make sure that we are talking about the true population parameters. All right, now step 2 in this 4-step process is checking the conditions. Remember, all tests refer to what all possible sample statistics could look like, and this is how we determine if our sample statistic is, well, weird or not. Remember, we need to compare our sample to what is possibly true for all samples, and that can only be done with a sampling distribution. So we have to go back and check those conditions. Now, there was a huge unit on sampling distributions, and maybe you want to go back and relearn it. Feel free to go back in my videos and do that. But remember, for the conditions, there's 3 basic things you got to check. The sample or samples have to be randomly selected. That will help me make sure I avoid bias. The sample or samples size needs to be less than 10% of the population. That's so I can assume independence. Now, I can make a whole video on just that rule, but I don't want to dive too deep into this. I just want to kind of skim the surface here. And then the last condition, the sample or samples need to be big enough. Now, that's where you got to be careful, because when you're working with proportions, to be big enough, you need 10 or more successes and 10 or more failures. Because with proportions, you're working with categorical variables. So you're not looking at numerical data. You're looking at data in the form of categorical stuff, like green gummy bears versus red gummy bears, or, you get my point. So I want to make sure I have enough successes and failures, 10 or more. When you're working with means, you either need your sample sizes to all be 30 or larger. That's what the central limit theorem says, that all sampling distributions will be normal. Or if you're under 30, that's when you kind of need to make sure that your data is already normal, or that your data has no major skewness or no major outliers, to make sure you're big enough. All right, the third step is the actual fun part. This is where you're actually going to create your p-value. Now, a p-value is what you're going to use to make your condition, or to make your conclusion. So let's first talk about what a p-value is. It is the probability of a sample statistic being more extreme than the one observed, assuming the null hypothesis is true. I know it's a little bit confusing, but a p-value is a probability. So let me go back to these kind of really terrible pictures I drew earlier. If this was my sample right here, and on the model you could see it's clearly very high, it's very far from the middle. Well, the p-value would be the probability that any other sample is more extreme than that. So it'd be the probability that I'm even higher than that. Let's just kind of show you another example over here. If this was my sample mean right here, then the p-value would be the probability that any other sample is even more extreme, which would, in this case, be lower than that. The phrase more extreme could be lower or higher. It all depends where you are. If you're already higher, then more extreme means even higher. If you're already lower, or more extreme means even lower. So a p-value is basically a probability above or below a certain value on a normal model. Now, how do you find a probability of being above or below a certain value on the normal model? Well, you can either use your z-tables or you can use normal CDF. So we actually get p-values from using normal CDF on our calculator. That's what p-values are. They're probabilities from the normal model. But you got to make sure you truly understand what they represent, because there's been plenty of AP, or there will be plenty of AP questions that simply want you to make sure that you know how to interpret a p-value. So again, it's the probability of a sample statistic being more extreme than the one observed, assuming the null hypothesis is true. Let's actually take a look at a couple of examples here. So if here is a p-value right here, right? Now this actually is not the p-value. This is just a representation of it. I'm just going to give you an example here. Now what we're saying here is, what is the probability that any other sample proportion is more extreme than ours? Now this means that our sample showed 33%, and we want to find the probability that any other sample is more than that. Now, of course, we're going to be referencing the normal model here, so we need to figure out where does 33% fall on the normal model, which means we need to calculate its z-score, and then from there we could use normal CDF, or you can use your normal tables to look above it, and that's going to give us our probability. Now, again, we're going to get an answer here. I don't know what it is. I'm just trying to give you an example. But in this particular problem, let's just say that we're looking at gummy bears that are green. So we'd say, okay, the probability that any other sample of whatever my sample size was will be green gummy bears greater than 33%, right? The proportion of green gummy bears in a sample will be greater than 33% is going to be my p-value. I know I'm going through that kind of quickly. Hopefully that makes some sense. So here's one dealing with means. So here we're saying, all right, the p-value is the probability that any other mean from a sample, any other sample mean x bar, is more extreme than mine. So 41 must have been on the low side, which is why more extreme would be even lower than 41. So once again, I have to figure out where does 41 fall on the normal model, or the T model if I have to use it, which is just like the normal model. And then I'm going to say, okay, let me go to TCDF or go to my T tables, if I'm using a T model, to try to determine the probability that I am below that. Here's an example when we're working with the difference, right? So I'm saying the p-value is the probability that any other difference between two samples, one of males and one of females, is more extreme than mine. So this means that my difference, the difference that I observed within my data, was 6%. So I'm trying to find the probability that it's less than 6%. Now, why less? Well, because 6% must have been less than what we thought. Hopefully you kind of get the idea there. And then another example here working with the difference of means is what is the probability that any other difference of sample means is going to be, again, more extreme than mine, which means the difference I saw was 3.5. So this is kind of how we represent p-values, but obviously you got to find p-values, right? Now, the idea here that I've been trying to get across to you is, go back to this first example. We have to figure out where does 33% fall? Where does that particular sample proportion fall on my sampling distribution? And to do that, we need to calculate a z-score. If we're working with means, with the T model, we call it a t-score. But this formula is actually given to you on the AP Statistics exam. This is the generic formula for what we call a test statistic, which determines where a statistic falls on the sampling distribution. So what we do is we take our statistic, we subtract the parameter. This comes from the null, right? This is what we thought was true, and we divide by the standard error of that statistic. Now, if you look at your formula sheet, on the back page of the AP Stats formula sheet is a box for proportions and a box for means. And on the far right side of that box is a column for all of the different standard errors. So if you're wondering what standard error formula you need to use, you have to first determine, am I working with proportions or am I working with means? Am I working with a single sample or am I working with the difference between two samples? Because that will directly tell you what formula to use for that standard error. Now, we're going to do some examples here in a little bit that are going to actually show you how to use that, but that's just a generic use of the formula. Now, again, if I'm trying to find the probability that a sample is more extreme than my sample of 33% green gummy bears, then I need to figure out the probability that a z-score is more extreme than, well, whatever the z-score is that I calculate. And then that's where I'm going to go to normal CDF or using my z-tables to actually find that probability. And with that probability, my p-value, I can actually make a conclusion. And that is, of course, step 4. Step 4 is making a conclusion based on the p-value. Now, a conclusion has 3 distinct parts to it, so make sure you get all of them correct. Now, remember, we're always looking for evidence to support the alternative. We either find it or we don't, but it's always about the alternative. It's never about the null. All right, so step 1 is identifying your p-value based on alpha. Alpha is your significance level. Most common values are 1% or 5%. Some problems will actually tell you what alpha to use. If they don't, you're going to use whatever one you want. I'd recommend 1 or 5%. So if your p-value is less than alpha, you need to tell me that. My p-value is less than 0.01. Or maybe your p-value is greater than alpha. My p-value is greater than 0.01. Now, if you determine that it is less than your alpha, that's when you're going to reject the null, because that means that what you saw was significant because it has a very low probability of occurring. So when you reject the null, the next thing you're going to say is, because I'm rejecting the null, there is significant evidence that the alternative is true. But of course you want to say that in context. Right now we're just being very generic. If you determine that your p-value is greater than alpha, that means that your test statistic was not unusual. It was not unlikely. In that case, we're going to fail to reject the null, meaning there is not enough statistical significant evidence that the alternative is true. But gotta say that in context. But note that's always about the alternative. When I give that final statement, I'm either saying, yes, the alternative is true and I have evidence to support that, or the alternative, I'm not going to say the null is true. Don't you dare ever say the null is true. I just don't have the evidence to say that the alternative is true. It's always about the alternative. So once again, I have seen so many AP multiple choice questions where they give you the p-value. They set the problem up for you. You don't have to do steps 1, 2, 3. You just have to choose the correct choice. So make sure you first compare your p-value to alpha, determine if you're going to reject or fail to reject the null, and then what that means. When you reject, you're saying there is significant evidence. When you fail to reject, there is not significant evidence about the alternative. Never choose something that references the null. All right, a couple more details until we dive into a couple of examples. I do want you guys to see some examples to help you out here. All right, now, first other idea here is error. This is actually a pretty big topic, probably going to be on multiple choice for sure, maybe an FRQ. But error is when you do something wrong. Now, I don't mean like a math mistake wrong. I mean like realistically the wrong decision was made. Listen, don't worry about if you did this or didn't do it. You just have to understand the possibility of it. So a type 1 error is when in actuality the null hypothesis is true, but we reject it. So anytime you reject the null hypothesis in favor of the alternative, you are possibly making a type 1 error. So if your conclusion is, I'm going to reject the null, there is a chance that that null was true, so you're doing the wrong thing, which means you might have made a type 1 error. Did you do it? Did you not do it? Don't stress too much about it. Type 2 error is the alternative is true, but we fail to reject the null. So we keep a null that's actually wrong and that the alternative is true. So anytime you fail to reject the null hypothesis, you are possibly making a type 2 error. So when your conclusion is, darn it, I'm going to fail to reject the null, I don't have enough evidence the alternative is true, there is a possibility of maybe the alternative really is true, meaning that you made an error. These errors are really truly hypothetical. You don't have to worry about did you make it, did you not. It's just the idea that sometimes we're not 100% sure. I mean, no test is locked tight. We're still using a sample to make a judgment about the population. So maybe we're wrong at the end, and that's the idea of these errors. Now, with this also comes power. Power is the exact opposite of type 2 error. The alternative is true, and we reject the null in favor of the alternative. This is making the right decision. This is doing the right thing. The alternative hypothesis is true. Our evidence leads us to reject the null and say the alternative is true. This is doing the right thing. And the probability of doing this is power. So power is the complete opposite of type 2 error. Power is a good thing. We're always looking for more power. I mean, who doesn't want more power? A couple different ways to get more power. Number one, bigger sample size. And that should make sense because bigger samples are always going to be more reflective of the truth. And if the truth is that the alternative is right, then a bigger sample should hopefully lead us that way. The second thing we could do is actually increase our significance level alpha. I know this seems kind of weird, but if you increase your alpha, you're increasing the area that you're going to reject. Okay, think about that for a second. If you increase alpha, that means you're more likely to reject the null. If I go to an alpha of, say, 10%, that means I'm more likely going to reject the null because more samples are going to fall into that rejection zone, so I'm more likely to reject the null. And if I'm supposed to reject the null, then that actually gives me more power. So hopefully that makes sense as well. All right, so let's actually dive into a couple of examples right now. I'm not going to type up every single teeny tiny detail. I'm going to kind of detail. but I'm going to kind of just walk through it and then show some of the big work. But obviously a lot more goes into this problem than what I'm going to do on what I'm actually going to write, but I'm going to say the rest of it out loud. So the proportion of gummy bears that are green is said to be 23%. Stop right there. That's a proportion. That tells me right away I'm working with proportions. But we think it's more than that. A sample of 400 gummy bears shows 33% are green. Is there evidence that the proportion of green gummy bears is more than 23%? A sample of gummy bears. Never read about a second sample, so this is clearly a one sample test looking at proportions. So the first step one, I'm just going to name it. This is a one sample Z test for the proportion of green gummy bears, or the proportion of gummy bears that are green. Now, my hypothesis, my null is going to be, nope, it said it's 23%. The truth is still 23%. And the alternative is what I'm hoping to show, and that it is more than 23%. Whoop, I wrote the wrong thing there. Greater than 23%. Now, notice no p-hats, and these numbers are terribly written, but they're the same. Don't ever use your sample, in this case 33%, in your hypotheses. All right, step two is going to be checking those conditions. This is where you're going to say, all right, the sample needs to be random, so make sure it's random. 400 gummy bears needs to be under 10% of all gummy bears that this particular company makes to assume independence. And then we also need to make sure we have enough successes and failures. So let's see here. So if I have 400 gummy bears and 33% were green, 400 times point, well, I typed in 4,000, didn't I? 400 times 0.33 equals 132 green gummy bears. That means the remaining 268 gummy bears are not green, so both of those numbers, my successes and failures, are both 10 or more, so I'm good to go on being big enough. All right, now step three is the fun part. This is where I'm actually going to kind of get my hands dirty here and figure out what's going on here. So the first thing I got to do is get my test statistic. This is going to be a z-score, because when you're working with proportions, you're going to use a normal model. So I'm going to take my sample proportion, 33%, and I'm going to subtract what was the parameter, what we thought was true, and that was the 23%. And I'm going to divide by my standard error. Now here's the deal. You have to assume the null is true. So if I go, now this is where you got to be careful here. This is the only time. This is actually the one and only one problem. You got to be really careful what I'm about to say here. If you go to your formula sheet and you say, okay, I'm working with one sample proportion, you look at that row, the formula for the standard error is the square root of your p-hat times 1 minus your p-hat divided by your sample size. But I'm actually not going to use that formula. Why? I thought I was supposed to divide by standard error. Yes, but when you're working with a test and you're assuming that 23% is true, I'm actually going to use standard deviation. The standard deviation does not use p-hat, it uses the truth. That would be the 23%, 1 minus 23% would be 77%, divided by my sample size of 400. I'm going to use that value. Why? Because I am supposed to assume through that null hypothesis that the truth is 23%. And anytime you know the truth, you should use it in calculating your standard deviation. It's when you have no idea what the truth is that you end up having to use standard error. So I'm going to go ahead here and grab a square root. And well, that's not, what is going on here? Second square root. There it is. 0.23 times 0.77. That's simply 1 minus the standard, or 1 minus 23%. Divided by my sample size of 400 gummy bears, and I get 0.0210. That's going to be my standard deviation, actually. So now I'm going to calculate that z-score, 0.33 minus 0.23. I get 0.1 divided by the 0.0210, and I get 4.762. Now, if you know anything about z-scores, you're like, holy crap, that's a really high z-score. And it is, because now I'm going to find my p-value. Now, let's make sure that we properly identify my p-value. It is the probability that any other sample proportion is more extreme than mine. Mine was 33%. More extreme means more. Why more? Because 33% is already more than what we thought it should have been, 23%. that is equivalent to a z-score being more than 4.762. So now I'm going to go here and grab normal CDF, because that's what you do when you're working with a normal model. I'm going to start at 4.762, go to 99 here, and I could go to 999, doesn't matter. 99 is just acting as my infinity, and I get a p-value of, oh my gosh, that's low. That's going to be 0.00000095960, right? So 0.0000096. So again, very, very, very low. Meaning that the probability of seeing my sample proportion or more extreme on the assumption that the null is correct is extremely unlikely. So my sample is a very special sample that is very, very high. So what am I going to do? Well, here comes my conclusion. I'm not going to write it. I'm trying to make this video quick. I'm going to say it. First, step one, since my p-value of 0.0000096 is less than 0.01, I will reject the null. There is significant evidence that the proportion of all green gummy bears is more than 23%. Do I know it's 33%? No, that was just a sample. But since that sample was so unbelievably high, I believe I have evidence that it's definitely more than 23%. All right, let's do one more example here. A sample of 36 male police officers run an obstacle course with a mean time. Let's stop right there. I see the word mean. I instantly know I'm working with means. A mean time of 6.1 minutes and a standard deviation of 1.10 minutes. A sample of 40 female police officers. Whoop, whoop, stop again. Now I'm recognizing right away I have two samples. Now I'm trying to kind of get my ducks in a line here. The mean for the males was 6.1 minutes. The standard deviation for the males was 1.10 minutes. Okay. Now the mean for, oh, by the way, there was a sample of 36 males. For the females, the mean for the females was 5.25 minutes. The standard deviation for the females was 0.65 minutes, and the sample size was 40. Okay. Okay. So now what's the question? Is there evidence that the mean time for male police officers is more than the mean time for female police officers? Well, my data certainly shows that. The mean time for the males was definitely more than the mean time for the females, but those are just samples, right? Just because one sample was more for the males doesn't mean that it's always going to be more for the males. But that's exactly what I'm going to do. I'm going to try to conduct a test to see if that possibly is true. All right, notice how I kind of wrote down the information as I read it. That's super important, especially when you are clearly working with two samples. So once again, go to your formula sheet, flip it over. On the back, there's a box specifically for means. Top row is for one sample, bottom row is for two samples. That's where everything you need is going to be. All right, so let's start off with step one. This is a two-sample t-test. Why T, by the way? Because the only standard deviations I know are that of my sample, and William Gossett said the T models are just flat out better when that is all you know. Now, it's a two-sample t-test for the difference between the mean times that it takes male and female police officers to finish an obstacle course. Don't forget to give me that context. Then I'm going to write down my null. My null would be that the mean time for males, sorry to say it, no different than the mean time for females. And the alternative is what I'm hoping to show, that the mean time for males is greater than the mean time for females. Greater meaning that males are slower. Now, once again, notice that there's no X bars there. I'm using my population means mu. All right, step two, checking all those conditions. Both samples had to be random to avoid bias. Both samples have to be under 10% of the populations to assume independence. And both samples need to be big enough. Well, one sample is 36, the other was 40. And we know from the central limit theorem that as long as both samples are 30 or larger, our sampling distribution is going to be normal. Well, actually, in this case, it's going to be a T model. And that's okay. It's just like the normal model. Hopefully somebody taught you that. All right, step three is the fun part. This is where I'm going to find my T-score. Now, how do I find my T-score? Well, I got to first start off by saying, what was the difference I observed? The difference I observed was 6.1 minus 5.25. So that is a difference of 0.85 seconds. So I'm going to take the observed difference, and I'm going to subtract the parameter. What was I assuming the difference to be? Well, I was actually assuming there to be no difference, which is a big, beautiful 0. Now I'm going to divide by the standard error. Okay, how do I find the standard error? Well, go ahead and look up on your formula sheet. The standard error is that last column, 2 samples for means, and this is what you're going to find. The standard error is the giant square root. It is the standard deviation for the men, 0.65 squared, divided by the sample size for the men, 36, plus the standard deviation for the females. Actually, I have that backwards. Oh my gosh. This is the importance of checking your work. Lucky I just did. The standard deviation, I'm going to go back to it to show you. The standard deviation for the men was 1.1. So I need a 1.10 there, squared divided by the 36 men, plus the standard deviation for the females was 0.65 squared, divided by the sample size for the females, which is 40. Again, that formula is on your formula sheet. Don't be afraid to use it. All right, now I'm going to go to my calculator to get that value. I'm going to do 1.1. Boy, oh boy. Trying to type on, you have no idea what you're looking at here, but the program I'm using here makes this tough. 1.1 squared divided by 36 plus 0.65 squared divided by 40 for the females gives me a standard error of 0.210, and that's what I put right there. So now my t-score is going to be 0.85 minus 0.210. Oh my gosh, hold on. I'm trying to go too fast because I don't want this video to be too long and get you guys mad. Maybe I should just take my time. 0.85 minus 0, that's the numerator, which I guess I didn't really have to do, divided by the standard error of 0.210, and I get 4.048. 4.048. So now for my p-value. The p-value is the probability that any other difference between a mean of males and a mean of females is going to be more extreme than mine. Mine was 0.85. That's positive, so it'll be even more than that. Now, my difference was 0.85 minutes, but again, the p-value is the probability that any other possible difference is more than mine. And I found out that my statistic, my difference was a t-score of 4.048. So it'd be a t-score greater than 4.048. Now, how do I actually get my probability? Well, when you're working with t-scores, we're going to use t-CDF, just like normal CDF, but working with the t-model. I'm going to start at 4.048, going to an upper value of 99. Now, the only other thing that the t-model requires is William Gosset invented many t-models, so we need our degrees of freedom. Now, the actual degrees of freedom when you're working with 2 samples, the formula is kind of complicated. So we actually recommend that you do one of 2 things. You use the lower of the 2 degrees of freedom. So the men had 35, the women had 39. So we're going to use the lower of the 2, which is 35. You could also add the 35 and the 39 together to get your degrees of freedom. Neither are actually the exact formula for degrees of freedom when you're working with 2 samples, but it's totally okay. Don't stress over it. The AP Stat says you're okay to use either one of my suggestions I just made. I tell my students to use the smaller of the 2 degrees of freedom. And I get 0.000, got to move that decimal, 136. 0.000136. Now here comes my conclusion. Again, I'm not going to write it down, but I'm going to say it out loud. Because my p-value of 0.00136 is less than my alpha of, you choose 1%, 5%, it's clearly less, I will reject the null. That means there is significant evidence that the mean time it takes male police officers to finish the obstacle course is more than the mean time it takes females to finish the obstacle course. In short, on average, male police officers take longer to finish the obstacle course. Give that context in a rich, beautiful statement. All right, hopefully this helped you. I know that I didn't do examples of all of them, but I do have a really cool document that goes through all examples for every type of procedure. If you want that document, just email me at helpwithapstats@gmail.com and I can get you that document. That way you can see all possible examples. I know I didn't go through everything in this video, but I think I went through enough that could really help you do well on the AP exam. Best of luck to you. Please make any comments if you have any, and don't forget to like the video, especially if you think it helps you. All right, that's it.